So welcome everyone to today's webinar on working with contact constraints inside Autodesk Nastran In-CAD. My name is Matthew McKnight. I'm a tech specialist with Autodesk working out of the Melbourne office, and I'll be running through the content today. So I hope you enjoy. Let's get stuck into today's session. A quick look at our agenda for the morning, our upcoming webinars. Well, this is actually the last in the series of webinars. We will be holding some additional webinars potentially on a month-by-month basis, and these will be looking at specific topics of interest or things that we're noticing from day to day, talking to people about Nastran and the questions they have. So if you've got anything in particular that you'd like to see in the format of a webinar, then please feel free to email me, contact me in whatever form to discuss ways of that we can bring this content to you. And let's have a quick look at the agenda for today. So we'll just quickly run through, as we've done the last few weeks, why we use FEA and how it complements our design processes. We'll look at contact constraints in some details. We'll work through a number of examples. We've got 4 or 5 to work through today. And then we'll go to finish off the session with some further reference material and any questions that you might have. If you've got any questions, feel free to insert them in the question dialog box. Otherwise, let's get into this. So why do we use FEA? Well, more often than not, it's because we're trying to understand our designs, predict behaviours, or potentially even look at failure of our parts or the way they're acting, and to better understand them. So this is the primary reason why we're looking at FEA, is to answer a lot of the typical questions that we'll have day for day inside of our design, engineering, manufacturing environment. As we've talked about previously, it's best to incorporate simulation as early into the design process as possible for a number of reasons. Let's have a look at those and the reasons why. So as we have learned that it's often easier, it's almost easier across the board, to assume that during the conceptualization stage we can affect the design significantly, and the closer we become to production or releasing parts to production, the harder it becomes to make those changes. As a result of that, the costs incurred in making changes are inverse. So it's very cost effective to make changes earlier in the conceptualization stage rather than when a product has actually been released to market. And if we look at the design process, the majority of the costs are actually incurred during that testing phase, and this is also leads to lost time as well. So what we're trying to do is shift this lump back earlier into the process, and as a result we're able to more easily make changes, understand our design, predict behaviours, and then develop a better product to ensure that we're meeting the needs of the market. And so, here's a snapshot of some of the typical results of that, is that we get better quality parts, we lower our costs, not only the development costs, but potentially also the production costs of part, and we can reduce the time to develop products, enabling us to bring them to market sooner. Okay, so let's have a look at contact constraints, which is what we're all the predominant topic of today, though we will be talking about a number of other things as well. Let's have a look at the number of the various different types of contacts that Nastran In-CAD uses, because it's imperative to understand these so that we can then work through and set up our environment properly. So in the first type of contact is called a separation contact, and we've got a number of, on the left-hand side you can see there's 3 parts here, and we're looking at the way that they interact with one another. So the separation contact enables parts to move around and interact with one another. It's called a general contact in Nastran terms, but it enables parts to pull away from one another or press up against one another, effectively enabling them to act in much the same way as most parts do in real life. Further to this, we then have bonded contacts, or what's referred to as welded contacts in Nastran. And this is where we're actually telling bodies, faces, edges, entities that they have a bonded or welded contact with one another. So they're physically locked to one another. If one moves, the other moves. So there is a dependency on one another created in this type of contact. Sliding, no penetration, enables parts to slide. Sliding, no separation, enables parts to slide but not separate from one another. It's referred to as slide contact in Nastran. So this contact can take into account things like friction, which is an obvious addition to this type of contact as well. And then we get separation, no sliding, which is referred to as rough contact. So where you've got parts that will actually be able to pull away from one another, but unable to actually slide past one another. And then you get offset bonded, and this is often used in an environment where you're analysing plate structures where there might be weld gaps, or you might be using shell elements, and because of the way that the study is set up, there's gaps between shell elements, enabling you to create that offset bonded contact. So how do we define these contacts in the context of using Nastran In-CAD? Well, first of all, I want to point out the fact that when you create a new study, in this case it's a linear static study that we've created, we have an option here for contact data. And this is where you set up the default settings for generating your automatic contacts. So the type of contact that we choose, going back to separation, bonded and the likes, is specified here. And then we specify a tolerance, and this automatically assigns contacts to entities, so faces, which are within those specified tolerance. So the wider the tolerance, the more entities it will capture and the more contact types it will assign. Further to this though, you also have the ability to be able to assign contacts in both automatic and manual fashion within inside of each study. So not so much as a part of the study itself, but within inside of the study setup. So you can, we've seen the dialog box here on the study type, but you've also got the option to be able to detect automatic contacts. Now this is new for the 2016 release. It uses the CAD geometry to automatically detect and generate contact pairs, but it's an inventor-only feature. So if you are a SOLIDWORKS user, recognize that this feature is only available to inventor users. Inside the automatic contact pair generation area, and this is actually, there's two different types of automatic contact pairs. There's the automatic, which detects the faces and assigns contacts to them, but there are inside the manual contacts another automatic contact setting that enables you to apply contact automatically, and it's generated by the solver. Within here you can apply a tolerance, and this defines the maximum activation distance for the auto setting. And the default tolerance in this is a factor related to a reference dimension of the model. So it's relative to the size of your parts that you're trying to analyze, which makes sense if you're trying to analyze small castings or molded components versus large welded structures, then the tolerance adjusts to suit the geometry that you're trying to analyze. Further to this, friction can be specified as well. Note that, and this can be for any contact pair, that in using friction though, convergence is harder, and so it's going to take longer for your studies to solve. And so a good practice is to actually first test the model without friction and then implement friction for once you've actually understand that the model has been set up correctly. Apply your friction and then run your analysis. If we look at manual contact pair generation, there is an option down here. And manual contact pair generation is where we're actually specifying entities. We're choosing faces, edges in reference to one another and assigning the type of contact. And you'll note here that that there's a maximum activation distance. Now the distance This is used to assign contact between elements within specific limits, and it helps, using this method helps limit the number of contact elements. And note that when the maximum activation distance dialog box is checked, but it's left blank, it then uses the default value from the solver distance. Okay, so this is the distance you've entered previously. Otherwise, let's step into some examples and have a look at all of this stuff in practice, which is probably going to help it make a lot more sense. So here we are inside of Inventor, and you probably saw these examples. I'm going to run through a couple of examples that we used last week because they are quite relevant and nice and easy to begin with, and then we'll move on to some more advanced examples later on. So to activate our Nastran environment, just under Environments, click Nastran In-CAD. This brings up the dialog area. As I said, typically you would move left to right across the menu structure across the top of the screen, or top to bottom through the Nastran model tree. Our study is defined in the top section under Assembly, and all of our parameters are defined under the Model section towards the bottom. Note that the model area is more of a library where we can set up various different parameters and then include them in various different studies that we're running in the assembly environment. Okay, so here we have a couple of simple plates. They're actually the same plate. They've just been constrained together in an assembly, and we want to analyze them. So I'm going to step through that process. I typically step through using the tree structure here because it does give access to a few additional features that aren't available across the menu, such as concentrated mass, dampings, connectors, and the likes. So we'll work through this section here, and hopefully everyone's seen me using a combination of them both over the last few weeks. So we'll assign a new material, and typical, my dialog box are going to maybe show up on the other screen, but so the dialog box that shows up is where we can enter our mechanical properties of our part, thermal properties and the likes. In this case, I'm just going to choose a material from our material library, and in this instance I'm just going to use one of the favorites that's been previously selected and define it in the context of this as a parameter within inside the model environment of Nastran. Now to assign that to these bodies, I need to right click, in this case a physical property, say new. It brings up the dialog box, and because I'm going to assign this material to all bodies within inside this environment, I don't need to associate geometry. I'm simply going to go OK, and you'll find now that our physical property has been assigned inside the analysis, and we've got our material that's been assigned to that physical property. Let's constrain the part, so I'm going to fix it at one end here, and then we'll apply our load at the other end. And the force is going to be minus 1,000, so about 100 kilograms force on the other end of the plate, and go OK. One additional thing, and we saw this last week, I'm going to create a connector, a bolted connector, that will represent the joint between the two plates. So I'm going to choose this face here and this face here, or that edge and that edge, and you'll see here that we've quickly defined our bolt. If we want to, we can change the diameter of the bolt. We can add a washer under the top and a washer under the bottom, and that will specify for us. Note that the blue and red are just indicators showing a representation and not actually geometry that's being modeled. We've assigned the material here. If we wanted to change the material, we could either assign mechanical properties here specific to the bolt, or we could choose any material that had previously been brought into our materials area. Otherwise, I'm just going to go OK. Now note that I'm just going to run this by default the way that it's been set up, and go OK and see what happens. And we'll use this as a test case to understand a little bit more about contacts. So if I just turn on the displacement plot in this instance, and we'll rotate around so we're looking to the right, you can see here that the parts are actually interfering with one another. So what's happening here is the parts have got some freedom to move, but they're not taking into account one another, and you can see there's a small amount of penetration happening in the bottom right edge there, and that's not typical of what we would expect in a real life situation. So we need to look at resolving that. So the way that we're going to do that is we're going to define a contact. So contacts can be accessed in two areas, at the top here or at the bottom. And we've got surface contact here. So previously there has actually been a contact defined here, so I'm going to delete that one. And actually I'll just run that again to make sure that that contact wasn't affecting the results that we got, because I want to make sure that we're getting a true indication of the consequences of the change. So you can see it actually is quite quick to run. No, so there was a contact that was set up, but it was just floating around down in our model area. It's probably been created as I was setting up the study and just forgot to delete it. So, so you'll note here that we get the same results. We get that small amount of penetration down the bottom right where the parts are starting to move into the same space as one another, like we said, which isn't indicative of what we would expect. So what we're going to do in this case is we're going to define a manual contact. So we'll start with manual contacts and how they affect. So in this case, we've got a number of options for ways that we can set up a manual contact. And this is, like I said before in the presentation material, there's actually two ways of defining a manual contact. You can have an automatically defined manual contact, or you can have a truly manual contact which is defined. The thing about the automatic defined contact is that you can choose various different types of contact types. In this case we would choose separation. We can go through and assign tolerances, coefficients of friction and the likes, and then just hit OK, and it's a generalized application of that type of contact. So wherever contact is detected where these specific settings apply, the contact will actually be applied. If we want to specify contact though at a specific region, we can do that. And in this case is what I'm going to do is just to show you how we can specify a surface-to-surface contact between, say, that plate and that plate. I'm going to leave the maximum activation distance. You can leave that turned on. You can turn it off and notice that it turns to auto, saying it will automatically detect. I can change the type. In this case we want to make sure it's separation so that the parts will pull away from one another. Go OK. And I'm simply going to hit run then. That's all we have to do in this case, is run the geometry through the solver and wait for it to solve. Now this will actually take quite a in comparison to the original analysis, quite a lot longer to solve, because it's taking into account all those contacts. So it's looking at contact between various different elements, but you can see there it's still quite quick to solve. Let's have a look at the results and see if it's more indicative of what we would expect. And yes, that makes a lot more sense. So you can see here that the part is actually pulling around. They're facing, they're face on face with one another, so they're not penetrating into one another. So you would see that this is more indicative of the type of result that we would expect from a study of this type. So quick and easy setup there of our contact type. So let's have a look at this in maybe the context of a slightly different example. And again, it's an example that we saw from last week, but I think it's important to highlight these. So quickly, let's step through the creation of this setup. So I'm going to select a material. We'll choose from the favorites, go close, OK. So we've now got the aluminium 6061 assigned in our materials area. Let's assign this to our parts. Now I'm going to do this in a slightly different way. I want one body to be a solid, so I'm going to choose associated geometry and assign that to this body, and it's going to be assigned solid elements. Click on the new icon down the bottom. I'm going to choose shell elements, which is just specifying that we're going to use a shell element on some specific geometry. I'm going to associate it to some geometry, in this case the face, of that body, assign a thickness, in this instance 10 millimeters thick, and then go OK. So in essence we're saying we want to use shell elements on this face, and the shell element is going to be a representation that's 10 millimeters thick. Go OK. Note that we're using the same material for both of those, so they'll both be assigned the aluminium, which you can see once we expand the physical properties. Let's constrain the parts, so we'll just put a fixed constraint on the back face there. Let's apply a load. Now the trick to applying loads on shells is that you've got to choose the edge, not the face. So that face no longer effectively applies to the geometry. So we're choosing the edge. In this case we'll apply a load of maybe 1000 newtons in the Z direction and go OK. And notice that we have a gap here, so we need to take that into account. So I'm going to again specify manual contact, and in this case I'm going to specify the type of contact, and note because we're moving between a surface and a shell, I'm going to choose the surface and the edge of the shell that we'll use, and then I'm going to choose the contact type. And I'm going to use an offset bonded contact, and the reason being is this is going to give you a reasonably accurate representation of that gap in relation to the way we would expect it in a real life situation. I'm going to turn off the maximum activation distance where I would specify what it is, just have it as auto, and it will automatically detect and assign based on the properties or the parameters that I've specified. Otherwise, let's hit update all, and that'll mesh the part. You'll note here that we've got a solid mesh on one part and a shell mesh on the other. Hit run, and hopefully this should only take a few moments to run, and we can have a look at our results. Okay, so we've got our results. Let's have a look at our displacement plot. I'm not worried about stresses today. I'm really just looking at the interaction of these contacts, just to make sure that the contacts are being set up correctly. Another good way of determining whether your contacts are set up correctly is to actually animate your objects. So once you've run an analysis, animate them and look, do they act in the way that you would expect them to? So we can see here that the plate, the solid and shell elements are acting and interacting in much the way that we would expect them to. So this is maybe a good indication that the type of contact that we've defined here has got some reasonable accuracy associated to it. Okay, so that you'll notice there that again that the key takeaway from this example is the fact that having run this analysis, even though we've got maybe some weld allowance or because of shell thicknesses, we might have a physical gap in our model, we can take that into account, quickly assign a gap, but using our contacts, and then run an analysis on our geometry. Okay, let's go to the next example. And in this example, I'm not going to run through completely the analysis, but we'll actually I'll just jump out of Nastran. In this environment, I'm just going to set up but not run the analysis. Oh, actually, you know what? We'll see how we go. So let's assign some materials. So I'm going to go new, and let's select some material. And rather than use our favorites, I'm going to choose some materials. We'll choose an aluminium, and we will choose another alloy, maybe a 6061, and go close and go OK. So what we've done is we've now brought in the two materials that we want to use inside this study. We'll assign one material to the angle line and the gusset, and then we'll assign the other material to maybe the U-bend and to the welds. So let's do that. So I'll go new and assign, we'll choose the 2014T4, and we'll associate it to geometry. And we simply then choose the geometry that we want to associate to, in this case the angle and the gusset. I'm going to click new, which will keep the dialog box open for us, enabling us to then switch over to the other aluminium type that we've selected, and then choose the various entities that we want to incorporate. I'm going to choose the weld and the U-rod, and then go OK. So you'll see up here that we've assigned those two materials. Let's add some constraints to our geometry. So rather than a bolted constraint, I'm just going to fix these holes in place. I'm going to click the new option, and then I'm going to create a fixed constraint on the bottom edge here and restrict movement, but only restrict it in the x-axis. So what I want to do is I want to allow it to rotate around this point. I want it to rotate in any degree, so around x, y, and z. I want it to be able to translate as well, so translate up and across, but just not out. So that's the only restriction we've put in place, is to stop it from translating outwards. And you can actually see the little indicators there show the direction of restraint there. And go OK. Let's apply a load, and let's assume a load of minus 600 kilos or thereabouts, and go OK. We've just applied that to the top face of our U-hook. And finally, what I'm going to do is I'm going to use automatic contacts. So up here, we said before, this is a feature with inside of Inventor, and was new to the 2016 release, is the ability to be able to automatically assign contacts. So if I click on that, you'll see that it runs off, and it then defines a whole bunch of contacts based on the parameters of the geometry. In this case, it'll be the geometry that's face-on-face touching. Now the good thing is that all of these have been defined, and they've all been defined with the default of a bonded contact. You can see here that the faces have been specified, and we can go in and modify any of these individually in reference to one another. So if maybe this wasn't supposed to be a bonded contact and was actually supposed to be a separation, we could go and change that here and change activation distance and the likes, add friction if we wanted to. The only thing that I really want to be able to, the only thing that I really want to do here is just to suppress two of those contacts that have been defined, because the weld is retaining the gusset plate to the angle line, and we've actually picked up two faces that aren't bonded to one another. So I'm just going to suppress this face and this face here. So in essence, what it's doing is it's taking the face that's on the underside of the gusset, which had previously been bonded to the top face of the angle line, and we're just suppressing those so that they'll effectively have no contact defined for them. If we really wanted to, in this case, you could leave them unsuppressed and then just change the type to separation, which would mean that they would actually be able to pull away from one another like they would in real life, but not penetrate through one another, again, like they would in real life. But in this case, you know, we can just quite quickly suppress them. I'm not so concerned in this case. I'm just using, this is an example to set up the automatic contact constraints. Another thing that I'll do is show you the, because we haven't really talked about mesh settings previously or in all that much detail. If you click on the mesh dialog box, it brings up the default dialog area where we can adjust the element size, turn on it or off continuous meshing and the likes, and change the order of the element type. But what I want to do is go into the mesh table and have a look, and the mesh table has been brought up over here. So the mesh table then gives us the ability to be able to easily and quickly manipulate mesh settings for a whole bunch of different parts here. Now this is a reasonably small assembly, so it's quite quick and easy for us to make changes, but if you've got 20, 30, 50, 100 or more parts, then making changes is critical and the time associated with it. And this is where we can quickly and easily go in and modify our settings. So if I wanted to, I can come in here and select to make modifications on all parts, go in and assign maybe a 3.5mm mesh size, and you'll see that that's been migrated across all of the components or parts within inside this assembly. If I deselect that now and then go and modify, just say the welds in isolation, I can just modify one well, one mesh size without altering all of the others. Note, in this case I'm going to turn off continuous meshing, which means that the nodes, which sometimes where you've got contacts set up, can actually become bonded and tied to one another. So I'm just going to turn off the continuous meshing option here. And if I then select all of the elements or components and hit update, you'll see that it meshes those in the background for us. So we can use this as a diagnostic tool. So if we're having problems with parts that aren't meshing, then we can quite quickly come in here, isolate the ones that are or aren't causing us problems, and then go in and modify those in isolation from the other ones, making it a very efficient method of using this mesh generation tool. Once we've defined that though, it's then just a simple matter of hitting run. We've set up our mesh, we've set up all of our parameters, we've assigned loads and constraints, and our contacts have been defined quite quickly for us. And you saw there that we defined effectively around 8 to 10 contacts in a few seconds. And it's quite easy for us to distinguish, those from one from another, because they're highlighting often the various different contacts visually on the screen for us. So we'll give this a moment to run, and then we'll have a quick look at the results that we're seeing from the study. So. If anyone's got any questions, again, this is just a quick reminder. Don't forget that you can enter them. If we've got time at the end of the session, I'll answer them. Otherwise, I'm trying to make sure that I get back to everyone after the session with any answers that they might be looking for. So let's have a quick look again. I'm just going to display the displacement plot and have a look at an understanding of this. Yep, it looks like it's working the way we would want it to. I'm often working inside the edit environment with inside the results. That gives you a little bit more control over the information that's shown. So I can go in here and turn off things like element edges, all of our loads and constraint indicators and the likes, and then display the information. It makes it a little bit more easier to decipher. I can also switch between various different types of studies, so I don't have to go outside this environment to then go and access say a stress plot. I can quite quickly then switch over to a von Mises stress plot and have a look at what the stress is in my design. I can even switch over maybe to a safety factor of plot, which is something we haven't actually shown to date, but you can quickly turn on a safety factor plot. The good thing is you can obviously go inside of these and turn on max mins. I can adjust the number of contour bands that I'm showing. So it was 24 different graduations in the color band. We've now reduced that to 10 down here by simply going into this section here. And I can turn on the maximum and minimum as well. So if I wanted to make sure that I had a minimum of, say, 3 as my factor of safety, then I can go in and make sure that I've got a 3. Let's segregate out anything out that's over 10 and go OK. And you'll see now that we've got a clear indication of those areas where there is some concern. And you'll note that using the probe tool, that there's the white areas here are actually indicating areas of our design that are under the factor of safety for the part. So factor of safety in this case is going to be defined by the things like the yield stress of the material. Okay, so we've quickly set up that study, so let's move on. We're going through time fairly quickly. Got another 10 minutes each left, which will run through 2 additional types, and I want to introduce some more functionality to you. So we've got this little joint that's been defined, and you'll note that the part's actually been split down the center of it, and the reason being is because the part is actually symmetrical about that plane. It's not symmetrical top to bottom because there is actually a washer on one side or a nut and a bolt, but effectively through the center plane that's been split about, it is a mirror from one side to the other. So the good thing is that we can take advantage of this, and it means that we can run analysis and get results that are indicative of that if we would run it using, a complete assembly or complete components, but in a fraction of the time. So we're actually reducing the time that it takes to run these types of analysis. Again, let's step through and set up this study. So in this case, I'm going to select the material. Something that I haven't touched on before is if you go load database, it actually by default it'll go through to a folder inside your program folders area, and there is an NEI materials file there. If you activate that file, you'll note there's a whole bunch of materials that are available to you to use. These have been set up by the Nastran team as part of the development of the product. So you'll find that there's a whole bunch of different types of what look to be steel, predominantly steel material properties, but there's a whole bunch of these that have been assigned to this library. So I'm going to choose one of them in this case. We'll actually define a couple of different materials. We'll select another one from that same database. Let's choose a stainless steel and go OK. So we've now got a carbon steel and a stainless steel. Let's assign these to the model. So on the physical properties area, I'm just going to go new and then select the geometry that I want to associate to. I'm going to choose associated geometry. I'm going to choose this and that. So we'll make those two components out of the carbon steel. Let's click new and associate the stainless steel to the bolt and nut and go OK. So we've assigned these material properties. Let's add some constraints. So in this case, I'm going to add a constraint which is here, and we'll add a load again, which is at the other end. So it'll be a sort of a torsional load, but is actually causing shear on the bolt. And we'll apply, what load will we put on this one? Let's make it a 200 kilos or thereabouts. It needs to be the opposite direction, so we'll put a negative in front of it. Go OK. What else do we need to do? We need to define contacts. So I'm going to use the automatic contact generation and just go OK. And you'll see here that it's found a number of different contact types. So we've got various different contacts that have been defined. Now, like we saw before, these are all going to be assigned the default contact type, in which case it's going to be a bonded contact. But what we want to do in this case is we want to enable all of those components to rotate and move in relation to one another, even separate away from one another, but just not penetrate one another. So what we can do is change these to be a separation contact. So I'm going to quickly go through and modify the types to separation on these quickly. Fortunately, there's no way no way that I know of defining them if they've been defined in this fashion in the one process. So, and the last one. Okay, so the only contact that we've got a bonded contact is between the bolt and the nut, to assume that they're locked in relation to one another. Everything else has got a separation contact enabling them to rotate and move away or in relation to one another. Okay, so and the final thing we need to do is add one further constraint, and this is a symmetry constraint. And you'll notice down here that up until now we've been predominantly using a lot of our constraints fixed, pinned, and and some customization of the types of constraints. In this case, I want to apply a symmetry constraint that's going to effectively tell Nastran that about that plane we have some geometry that's symmetrical. So I've chosen all of the faces that have been split, and I'm just going to assign X symmetry. And you'll see it defines now a set of contact constraints that that will represent a symmetrical constraint for that geometry. Note, the one thing that I will note that I didn't mention before is that when we assign our load will be a factor of the symmetry. So if we've halved our part, then we want to half our load. So in this case, our true load might actually be 4,000 newtons, but because we're only using half the geometry, half the material, then we actually only assign half that load. Otherwise, we can just hit run. I'm going to use the default mesh settings and see what happens. And hopefully this shouldn't take more than a moment or two to run before we get a result. Take the opportunity to grab a quick drink. So there we go. So it was only a few seconds. Let's have a look at the final result. And again, I'm just using a displacement plot. It looks it's very hard to decipher because there's a lot of information that's going on here. So what I'm going to do is edit the plot. I'm going to hide some of the information that's being shown and then display that again so that we can better see what's going on and understand whether we're getting a true representation of our parts. So you'll see here that we're getting a true representation. Notice though that there's a couple of areas where we're getting sticking nodes that are sticking on our geometry. So this comes back to something that I spoke of before. If you're noticing that, it's because of a setting inside of your mesh settings where you've got continuous mesh turned on. What I'm going to do is change the mesh size as well. So we'll adjust it, we'll make it a little bit finer so we can see a little bit more detail of what's happening. Maybe we're a bit concerned because there's not enough elements through the thickness of material. Like I said, turn off continuous meshing. We'll hit update, that'll update the mesh geometry. You'll see that happening actually in real time in the background. Go OK, and then again we'll quickly run that and see the result of making those small changes to our setup here and the consequences of it. Warnings that you see there, I wouldn't be so concerned about them. We talked about this in one of the earlier sessions about a mesh and how do you know whether you've got a good quality mesh. We will be putting together a webinar hopefully in the next month or two that will talk somewhat about the various different types of warning messages that you can get and also the error messages so that you can help you problem solve some of the issues that you might encounter when you're setting up and running your models. Okay, so we're just finishing up, and there it goes. And let's have a quick look at our displacement results again as a comparison. We'll edit them, display. And note now that not only are we getting a little bit more detail because our mesh has been refined, but those instances where we were getting some elements that were effectively tying themselves to adjacent elements have gone completely. So if you are seeing that, then that's a good indicator that you need to go in and adjust your mesh settings. So otherwise, like I said, you can, another good thing to do is to animate your results to see visually whether they're reacting or acting and reacting in the ways that you would expect them to. Generally, this doesn't take much to run an animation, but you actually can access quite a lot of information from it. And you can see here how the components are acting in relation to one another, and that looks to have set up quite well. So again, looked as though we've done the right thing there. Just going to turn the animation off and finish that one and then move on to our last example. Okay, so here we are. Nastran In-CAD environment. Again, let's quickly assign some materials. We'll choose, I think we chose an aluminium. Choose a steel. Okay, we'll assign those. Steel is going to go to the pin, aluminium to the handle, apply a load, that face. The direction is going to be in the Z direction. We'll do 5. Okay, let's add, like we said before, a constraint, a couple of constraints. We'll add pin constraints to either end of our pin. We're going to add a symmetry constraint with the end face of our part. So there's our 2 constraints. Let's define a connector. So we're going to define 2, a rigid body, one between here and the edge, and then another between here and that edge. Let's pick up our contact. We'll define a manual contact. Surface to surface, it's going to be that surface on that surface. We're going to have it automatically detect separation not bonded. Go OK. Here's our surface contact that's been defined. And let's hit, let's maybe change our mesh size. Oh, we'll just leave it. Turn off continuous, hit update. We'll have a quick look at it, see what it looks like. Yeah, doesn't look too bad. Let's hit run and give it a few moments and see what comes of this. So what we would expect is we've effectively got this handle is almost free to move, because the only constraint, the fixed constraint that we have is on the pin. So the pin can't move either end. It'll be able to lift up is what we would expect. And as the handle lifts, effectively there's nothing tying the handle to the pin other than the contact constraint. So we should be expecting some pretty funky things going on between the contacts in this case to simulate the interaction between the 2 parts. And we're a few minutes out, so let me just, again, any questions you might have, shoot them through. Otherwise, this should only take a few more moments, hopefully, to finish up before we can have a quick look at it. I might show, whilst that's doing, talk about some further reading that you can be doing in your spare time. So if you're after some more information about Nastran In-CAD, the forums, the Autodesk forums, are full of information, reference material that's uploaded by a lot of technical specialists and support personnel, but also from users that are using the product, asking and answering questions between one another. It's also a good area where you can submit your ideas for ways to improve the products as well, using what's called Idea Station. Beyond that, there's regular updates from the simulation team on Twitter. You'll also find that the simulation team are updating on Facebook regularly information that's relative to Nastran and related products, and there's often information that's being uploaded to the Autodesk Simulation YouTube channel as well. Beyond that, we also have a local Future of Making Things group inside of LinkedIn, so please join that group. There's a lot of interesting information that's posted up there that's relative just to manufacturing, and predominantly manufacturing in our local area. And then obviously if you have any questions, then feel free to contact me directly. My details are up on the screen. I'm more than happy to answer your emails and calls as required. Otherwise, I did hear Nastran finish up, so let's have a quick look at it and have a look at the reaction that we're getting. And you can see here that it looks like it's doing what we would expect it to. Again, let's go inside of our edit environment where we can turn off a heap of things that we don't need to see. Let's display our displacement plot here. Have a look at the reaction of our part. And like I said, sometimes animating geometry can give us a really good insight into how our parts are reacting and help us problem solve if we think that the part has been set up correctly or incorrectly. So you can see there that we've actually got a very stiff pin. The pin's actually not moving much at all. Our part is actually deflecting quite a bit. And it's sliding along the pin there, so you can see that we're getting a reasonable amount of interaction along the lines of what we would expect. If we wanted to, we can quite quickly, say, turn on our stress plot and have a look at the stress through the parts and understand what's going on in this case. The other thing to note as well, you can get reaction forces as well, so contact forces as well. So if we wanted to, we can go and turn on our contact forces and look at the forces that we're actually getting back on our pin and through our geometry. So this gives us an understanding of the interaction at the interface of what's happening in those areas as well. Otherwise, again, I'll just switch back to the end of our presentation. We actually have run out of time. We're bang on 12 o'clock, which is good timing. I thank you all for your attendance. Wish you all a good day, and hopefully we'll see you at another Nastran or Autodesk related webinar in the near future. Thank you.